going to be telling us about the possibility of having superconductivity in the presence of high magnetic fields. So thank you.
Thank you. So I decided to make this talk as qualitative as possible for the purposes here. But I want to mention at the outset that the results that we obtained are very quantitative in nature, but you do want to see slides full of Green's functions and so on. So please ask. Okay. I have a few of them for you.
Organize a private meeting.
Take that off. So the topic is superconductivity in ultra-high magnetic fields. And of course, we know that in general, magnetic fields are the enemy of superconductivity, right? They destroy superconductivity. So let's briefly go over some general features of type 2 superconductors under normal magnetic fields, not ultra-high. So this diagram has appeared throughout most of my grad talks. So it shows a phase diagram of a typical type 2 superconductor. At very low magnetic fields, you have complete expulsion of the magnetic field from the deep interior of the superconductor. This is the famous Meissner phase, right? And then above the lower critical field, HC1, you have penetration of magnetic field in terms of quantized flux tubes. This is the so-called Abrikosov phase, right? The resistivity here is still 0, but the magnetic field penetrates the superconductor. And then once you reach the upper critical field, HC2, then you cross over to the normal phase, and then you get metal, let's say. Okay, so any questions on this? This is a pretty common textbook example of how type 2 superconductors behave in magnetic field. Now, this diagram is a reproduction of the work done by my thesis advisor Levitt in 1986. So let's see what it shows here. The question I want to ask is, under what conditions, if any, can superconductivity persist in high magnetic fields? And by what I mean by high fields will be brought into several examples throughout my talk. So the first part of the curve here is pretty much what you have seen on the previous slide, right? As I increase the magnetic field, the critical temperature goes down until eventually at the upper critical field, superconductivity is destroyed. And then you might have some fluctuations here. Superconductivity starts to restore. This restoration occurs because of a quite a general phenomenon called dimensional crossover, and I will explain what that is. So, superconductivity actually can be restored under high magnetic fields, and as the field grows and approaches infinity, the transition temperature approaches the zero field transition temperature. Essentially, infinite magnetic field is equivalent, as far as bulk properties are concerned, is equivalent to having no field at all. Okay. Now, of course, there are certain limitations to this because we cannot have paramagnetic splitting, right? If we have a spin singlet state, then magnetic field will align the Cooper pairs and destroy superconductivity. So there, one of the fundamental assumptions that goes into this theoretical curve is that superconductivity does not have paramagnetic limit in this case. So for example, a spin triplet superconductor could exhibit a behavior like this one. So in this talk, I want to think about superconductivity not just as some kind of a phenomena specific to some compound like a metal alloy or an organic compound or even just mercury. I want to talk about superconductivity as in a more general sense, as an ordered phase of matter that possibly competes with other ordered phases. right? And what are some of the other order phases? Well, we have spin and charge density waves, we have antiferromagnetism. Which phase is preferential as the ground state is an important question, right? And then a specific material has to be studied in order to answer that question. So I drew this diagram as an imitation, not quite exact, but this will be for an organic superconductor of the Beechcraft salt family, which shows the existence of several ordered phases. What we're going to focus would be a slice here. So there are three parameters here, right? Experimentally, usually we can easily vary the temperature, the pressure, and the externally applied magnetic field. And so these are the parameters that we vary. Age increases this way out of the board, temperature increases up, pressure increases to the right. I want to focus on a slice of constant pressure that's drawn on this rectangle, which shows normal superconductivity and then the reentrant phase. So now, what is different in our work compared to the theoretical prediction of Levin of 1986? Well,
what's an ordered phase?
An ordered phase is essentially you have a phase transition, right? You can have, let's say, above the Curie point, right? It's inside disorder. Below the Curie point, you have antiferromagnetism. A simple, more familiar example. But superconductivity is also an ordered phase because above the critical temperature, you don't have pairing of electrons into Cooper pairs. And below the critical temperature, you undergo a second order phase transition and electrons become coherent. So it becomes a coherent state. So that's an example of an ordered phase. Spin and charge density waves are also examples. Let's go over a little bit about this phenomena on dimensional crossover and see how it can affect superconductivity, and in particular, how it can help restore superconductivity in high magnetic fields. So we always assume a tight binding approximation for a crystal, right? And we have here a highly anisotropic layered conductor. So we have the most conducting axis is the x-axis, and then you have also the perpendicular direction along which the magnetic field is applied, and you have the normal to the layers. So we're going to assume that V Fermi is the dominant component of the Fermi velocity in the x direction, and then the interchain and interplane velocities are small. Okay, so an isotropic layered compound. Now, so we apply a magnetic field perpendicular to the most conducting axis. And let's talk about this qualitatively in a quasi-classical way. So we have the Lorentz force. So in principle, we can calculate trajectories because from the energy, we can take derivatives, we find velocities, we integrate them, and what we get is that a typical electron quasi-classical trajectory, the amplitude of it is inversely proportional to the applied magnetic field. And it's periodic. Which means that for a high enough field, you are squeezing electrons down and confining them to the layers. But if that's the case, then there is practically no flux penetrating the Cooper pair. And therefore, orbital destructive effects, which kill superconductivity, are minimized in this case. And that leads to the restoration of superconductivity under high magnetic fields. This is very, very qualitative explanation, but I want to say it just to make sure we're on the same page. Any questions so far? Okay, now, we want to explore the case where, one, the magnetic field is not just perpendicular to the conducting chains, which are along the x-axis, but also has a normal component and two huge magnetic fields of the order of hundreds of Teslas. So what happens in this case? Again, talking qualitatively, we can perform the same kind of analysis, and now we'll find that using the Lorentz force equation and the expressions for the velocity, both the y and the z directions are being tightly squeezed in by the magnetic field. Okay? Which means that if the field is very large, what you have essentially is kind of one-dimensionalized electron motion along the chains. What kind of fields are we talking about? Well, we're talking about the fields where these are basically the amplitudes of the electron trajectories. So these amplitudes have to be small, much smaller than 1. And effectively, you want to have the coherence length in both the y and the z direction. Coherence length is basically, you can think about it as the typical size of Cooper pairs, or the typical length scale on which superconductivity varies, right? This coherence length should be small compared to interlayer distance, but also compared to interchain distances, right? So we're squeezing them in both directions. So we call this the quantum limit. Why? Because the methods employed previously to solve the restoration of superconductivity in the case where you have a crossover from a 3D to 2D, right, on the planes, used quasi-classical or Iconic approximation. Here we want to try to attack this problem using fully quantum mechanical methods and see what comes out. Any questions?
Well, superconductivity is impossible in one dimension, so what does that imply for this possibility?
So we are, okay, so of course, it's impossible. But now we are assuming that there is enough delocalization still for Fermi liquid picture to be restored at some point. Of course, there is a competition for, let's say, a spin density wave, Lantinger liquid effects, but one of the assumptions we're going to make in order to make progress in this case is that although the squeezing is tight enough to restore superconductivity, there is enough delocalization for the Fermi liquid picture to survive. Does it make sense? Now, so let's go over features of the quasi-classical re-entrant superconducting cell. Of course, so no paramagnetic limitation, right? We're assuming a combination which is insensitive to spin splitting. So we had a dimensional crossover which is from a 3D to 2D planes. But in the case of the quantum limit, the difference is we're going from a quasi-one-dimensional normal metal to a one-dimensional, quote-unquote one-dimensional superconductor. Okay, so the goal is to solve the fully quantum mechanical problem, and the next slides will be a little bit technical, but I will try to explain what everything means. So for quasi-1D compounds, typically the Fermi surface is two open sheets which are slightly warped. They extend in a z direction, and they're centered at plus and minus p Fermi, right? This small warping is due to these terms, and the linearized tight binding model will have just the energy with respect to the Fermi energy as the first term, and then these two additional perpendicular hopping terms. Magnetic field is going to be perpendicular to the conducting chains and also have a small component normal to the conducting planes. the Hamiltonian is obtained by a method called pilot substitution, where we essentially replace the momentum by its canonical momentum, meaning that you include the vector potential in it. Anyway, the important thing is that this Hamiltonian here does not have any paramagnetic terms, as one of the assumptions, and the Schrodinger equation can be solved for the exact wave functions. So after we do all that, we arrive at something called the gap integral equation, which is derived from Garkov's equations for unconventional superconductivity. So what does this pairing diagram here mean? So we have pairing of spin triplet equal pairs, right? So you have, if I can go back to the Fermi surface, one slide, you have an electron right here paired with an electron on the opposite Fermi surface, an electron here paired with an electron to the other side. Okay. G here is the effective electron coupling constant. You can think about this as, let's say, some kind of a potential interaction which is constant near the Fermi surface, similar to how BCS did it. So after we plug in the wave functions and calculate the Green's functions, we arrive at this gap integral equation. Delta here is the order parameter for superconductivity. But since I pasted it in here, let me explain what the terms mean, actually. Okay, first, if the magnetic field is zero, no magnetic field, these are Bessel functions. They would be absent in this integral equation. So the presence of the Bessel functions arises due to presence of the magnetic field. Omegas here are the oscillation frequencies. They're proportional to the magnetic field. So you can see if H is 0, omegas will be 0 here, and the Bessel function of a 0 argument is 0. Now, what about these trigonometric signs inside? These arise due to quantum effects, specifically Bragg reflection of electrons from beryllium boundary zones. In the quasi-classical case, these signs would actually be absent in this case. But we want to solve the fully quantum mechanical problem. That's why it's important not to make a quasi-classical approximation in this case. So delta is the order parameter. It appears inside the integral and outside the integral. The question is, can we obtain an analytical solution when this condition is satisfied, meaning that when electrons are squeezed tightly enough along the 1D conducting chains? The answer is yes, because in that case, when the magnetic field is really high, you see these are all 1 over h here, because omegas are proportional to h. So the amplitudes here are much less than 1, because think about it like this. The Ty are the transfer energies popping. They are small, on the order of, let's say, kelvins. But magnetic fields are huge in this case. So to make the units correct, you should express the magnetic field also in Kelvin, but this ratio will come out to be 1/10 or less. In which case, the Bessel functions can be expanded and up to, let's say, a second non-zero term. So that is how we approach to find the analytical solution to delta. Now,
Can I
what
ask
are the
a
questions?
It says that order parameter is nodeless. Is that possible when you have a triplet spin wave function?
So the order parameter in this case is assumed not to have zeros on the Fermi surface, but it does change sign from once, so if I go back, so the order parameters changes sign when you switch to them, but it's nodeless on a sheet.
Okay.
That's what I meant. Okay, so we did actually obtain the solution, and it confirms our predictions. Ly and Lz are the lengths in the y and the z direction. You can think about L times the lattice constant as being the size of the typical size of an electron wave function, or its spatial extent. So we obtain an expression for the transition temperature as a function of magnetic field. And it has this expression, and one of the properties here is that if we take h to infinity, we get T equals Tc. Which means infinitely high magnetic field is the same as no field at all. But that was actually evident even from this equation. Because if h is infinite here, well, signs are bounded. They are at most 1. So if h is infinite, omega goes to infinity here. So you have 0 inside the argument of a Bessel function. But Bessel function of 0 is 1. So you essentially get the same thing as you would if you have a magnetic field of 0 inside. So this confirms our expectation that superconductivity should be restored in this sense. Now, what about the geometry? Because the field was at an angle. Remember, it had a perpendicular component, and also it had a normal component to the planes and had a perpendicular component to the chains. Well, we take the example of a possible triplet superconductor that we studied thoroughly throughout the last few semesters, which is the lithium molybdenum oxide. It's called purple bronze, and it's a transition metal oxide. And we already calculated the band parameters using the available experimental data from Mercurian collaborators, which I presented a couple of talks ago. So what we find here is that the transition temperature, where superconductivity restores, actually has an angular dependence, but very weak angular dependence. You can see that at 700 Tesla, the maximum transition temperature occurs at around 58 degrees. And at 500 Tesla, the maximum seems to persist. So the angular dependence is not very sensitive to the applied magnetic field, but the critical temperature is. So we suggest to use this result to test and possibly unequivocally prove the triplet pairing nature in this compound. But in a more generalized sense, we have shown that yes, superconductivity can be restored under ultra-high magnetic fields as a one-dimensionalization, or the quantum limit that we call it. But the magnetic fields are really high. So this would be the geometry, 58 degrees. This is the optimal, at least, which will give you the optimal critical temperature. The higher the critical temperature, the easier it is to measure experimentally, supposedly. So these intersections are where the quantum limit is reached in this case. So for example, for 700 Tesla, it's about 1.7 Kelvin. But 1.7 Kelvin is not too far away from the actual TC of this superconductor. There are fields of this magnitude available experimentally. In 2014, 730 Tesla was achieved in Japan as a destructive field. So the sample is destroyed. It's explosive, basically. And a pulse non-destructive field actually at Los Alamos, the order of 100 Tesla. For extraterrestrial superconductivity, we know that neutron stars, well, we hypothesize that neutron stars have a superfluid component with neutrons and a superconducting component with charged particles. And it will be interesting to see, to know how these ultra-high magnetic fields affect the dynamics. And so it's not just something you want to do in a lab, but it has a more broad kind of a theoretical interest.
I would expect it would be quite difficult to make the measurement if you're using a pulsed field, right?
Yes, these fields last for, I don't know, microseconds or fractions of a millisecond.
So that's,
Yes.
I mean, that's a very difficult measurement to make, especially if you destroy your sample each time.
Yes.
Do you have, I mean, do you have some realistic proposal for how you could measure that?
Unfortunately, no. Unfortunately, I'm not familiar exactly with the mechanics of these kinds of measurements, but I know that these fields are already available, and hopefully somebody will be able to figure out how to detect at least traces of superconductivity.
Okay, so I guess in a related question, how does a critical reentrant field depend on the material?
We studied this specific material.
Would you expect it would vary based on?
Yes, of course. For a different material, it will be a different critical field.
So is there some hope of finding material where the field is like on the order of 50 Tesla?
We did some conjectures, and actually fields of order 40 Tesla even have signatures of restoration of superconductivity in this compound, even in this compound. So again, 45 Tesla would be something
Yeah,
to
I
look
certainly
at in
agree
this
that's
case.
possible.
Yeah, yeah. But even at 40 Tesla, even experimentally, signatures of superconductivity have been found in this specific compound.
Reentrant.
Yes, reentrant.
Can you go back to your original schematic showing the reentrant superconductivity?
Yes.
How do you make a magnetic field that large? It's not just a big electromagnet, right? What do you do?
For the explosive ones, set off a bomb. Quite literally.
This one?
Yeah, so what's that wiggling in between the HC2 and the...
This wiggle, I put it in by hand to include the possibility of some fluctuations. Just like you said, would it be possible to have superconductivity at lower fields? And what about also the spin singlet state? What if the paramagnetic limit spin splitting can be actually suppressed somehow? Is there possibility of a reentrant state when paramagnetic effects are suppressed? The answer is actually yes. There's a work by Levitt which proposes the so-called hidden reentrant superconducting state. But this is not something quantitative. I just put it in to indicate some fluctuations.
Okay, so to really test this effect, it's more than just seeing that the superconductivity comes back. You have to see that it behaves, that the TC behaves in some specific way.
Oh yeah, well the TC has to reach eventually at high magnetic fields. The TC has to reach the value it has at zero field.
Sure, but my point is that you can't really go very high in magnetic field right now. So even if you decide to turn back on, that wouldn't be enough to confirm this hypothesis, right? You really have to test it over a range of fields.
Of course, because we calculated the maximum, but you could do 100 Tesla. Of course, the TC would be much lower, and consequently more difficult to measure in this case, because the sample just gets heated up and it jumps into normal state, and then you lose superconductivity. But even just the normal TC of this compound is 2.2, which is already pretty high. Was one of the reasons why things like night shifts and all those things could not be measured in this case because TC is pretty low. But yes, so if somebody can detect reentrance at a lower TC, it will still confirm. Lower TC and consequently lower magnetic field.